Alright, time for another DraftPhysics.com video presentation. Alright, so his physicist Michael has put up a lever launcher and angular momentum testing physics video. Now, we talked for an hour and a half about all this stuff. I mean, angular momentum wasn't the subject. All we need to know is what's the velocity and mass of the object going into the experiment, and what's the velocity and mass of the objects going out of the experiment. It's that simple, and of course he's trying to convert it and pervert it into some other question. Now, as I pointed out in our discussion before the experiment, and as I pointed out in a couple of videos I made before he did the experiment, you really have to first figure out how much the lever is going to steal from the experiment. And your first test would be just to see if you can make 100 momentums go in and get 100 momentums out. That would be the first thing to do, is to hit the same mass card on one side, same distance from the fulcrum, and then see if the other side of the fulcrum produces a cart going anywhere near the same speed with the same mass. That would be the first experiment to do. Now let's see if he did it at all. I'm predicting he didn't. But whatever, we'll see. So far, I'm 9 minutes and 54 seconds into the video, and it's a bunch of jargon about some sort of angular momentum, which really just doesn't make any sense. Angular momentum is momentum. So if you're conserving angular momentum, you're conserving linear momentum. You really can't do one without doing the other. So I don't understand his whole obsession with this angular momentum crap, when what we really want to figure out is if levers conserve momentum, or do they conserve kinetic energy, whatever that is. I guess I should add, I'm a little further in. He's doing all this talking, what we're going to predict, and all this. He's already done the experiment when he's making this video. So he already knows the results, and he's talking as if it's all kind of unknown, which is just sort of bullshit. I mean, it's not sort of bullshit, it's absolute bullshit. I mean, to pretend he hasn't already got the results, and he's just, come on. Alright, so he's going through all this mathematical jargon of squaring this, blah, 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 all this crap, when all the experiment is supposed to be testing is the comparison between kinetic energy and momentum. You just need two formulas. All you have to do is figure out what the velocity and mass going in is and what's the velocity and mass coming out is. That's it. There's nothing more here, and he's turned this into some convoluted pile of crap, frankly. I mean, just really annoying. So he has shown the bar and stated that he's done a calculation based on its mass, what its moment of inertia is, or somehow what it's going to consume out of the experiment. And frankly, that needs to be tested, okay, because he has a bearing on the lever. And how well it actually functions is what he's got to test with an actual experiment, not with a mathematical statement. But whatever, it's just more bullshit. So for whatever reason, now he's talking about measuring the angular rotation of the bar. And what value would that have? It has to be going the same speed as the cars are going. So I just don't understand. I just can't understand why he's talking about angular momentum. Alright, so the angular momentum being conserved doesn't mean anything. It's obviously, he's saying that this side, when it comes crashing in, it's going to decelerate, and this side's going to accelerate. Of course that has to be conserved. How could it not be conserved? This side has to accelerate the same speed that this decelerates. It's an insanely moot point. It really doesn't have anything to do with this experiment. The whole question is what rate does this decelerate? What rate does this accelerate? That's all we want to know, is what speed is it? the deceleration of the one side is going to be the same as the acceleration on the other side. I mean, duh. All right, so he's just pointed out that his bar is not on the center of the fulcrum. So it is behind the fulcrum as the carts hit it. So in a sense, that's better than in front of the fulcrum. But I have to think about it, but I think that's better. All right, on the bright side, he has 3 cameras, so that's all good. But we'll see. We'll see. All right, so this looks good in the sense that he's doing this side by side. Now, if these are the same mass carts, now that'll be the problem, is he probably doesn't have the same mass carts, but we'll see. I'm hoping. All right, so we probably shouldn't have bothered. The inelastic collision, he's putting a blob of clay on the damn cart. I mean, really, fuck. You can't, I mean, a deformable object. He's putting a deformable object on the front of the cart, and you're just saying, well, how is that going to work? We want to try to get the energy from one cart into the other cart. If you deform some clay in the middle of the experiment, guess what? There's no chance you're going to get the energy from one cart into the other cart. So, this is worse than his first experiment. Put a little piece of like a rubber eraser on it or something because he's worried about protecting his carts, which is just sort of bullshit. They're really not going to be all that taxed. But what he should be doing for an elastic, if you want to get a hard elastic collision, that's what we're after, is a hard elastic collision. Okay, not a bouncy collision, a hard elastic collision, where all the energy has to go back into the objects that were moving originally. And here he is just, this is the game killer right there. That blob of clay will make kinetic energy conserve because guess what? It's going to absorb all the extra energy. I mean, all half of the energy of the system is going to be used up by the clay. I mean, it's just such a bad idea. It's so silly. How could you possibly you wouldn't do that to a Newton's cradle. Oh, I'll put a blob of clay on one of the balls and we'll see how well it converts the energy into the other ball. I don't think it's going to go anywhere, is it? No. I mean, just amazingly bad. So all this for nothing. I mean, that's right there. So all he's going to do is spring experiments and clay experiments. Well, fuck that. That's nothing I described. That's not the experiment I wanted to see.
Methods to make it more elastic. This still seems to be the best one, even though there is definitely some friction on those springs. We do get a little bit of energy loss from that. I'm expecting between maybe 15 or 25%, somewhere in that range for energy loss. But this should be, closer to the elastic case. And when we want to go for the inelastic case, I'm going to flip this around and basically put this clay on the front of the cart. So make a bumper on the front of the cart. So when the cart hits the end of the track or hits the fulcrum, that's going to compress some of this Play-Doh, and that's going to give us closer to an inelastic collision. So I think those are the main things.
You heard that, so I'm just saying. So he did it with a spring, and it appears to be right in line with what I would predict, in the sense that he's got a pretty good energy exchange. He's able to get the energy from one cart into the other cart, even though there's a spring. So the amount of energy that went into a reflection was very small, even though he's using a spring. So that's a big surprise. So we'll see where it goes. So perfectly consistent with what you would hope would happen, which is most of the momentum was exchanged from one car into the other car. All right, so really not bad. Just a 10% loss of the total momentum. 2% in a reflection, and the rest in the lever moving, no doubt. So that's not bad. All right, so the fact is this experimental setup works pretty good. It's a small, less than 10% loss to the lever. So that's a pretty good minimal amount. And frankly, the whole experiment's ruined because of the stupid clay idea. Right? So the clay is just going to ruin it. Yeah. Take all the fun out of it. So we'll have to just wait and see. If they all have clay on them, forget it. I don't even know how you could think it could. You're hitting a little tiny bar with a hunk of clay. The bar is just going to sink into the clay and make a mess. So this is the first of the clay experiments. Gigantic flaw, right? I mean, he just killed a whole bunch of the momentum, and didn't transfer the energy because of that reason, and so some of the cart is still moving in the same direction. So the first cart just kept going at a slower velocity after the collision, which doesn't make any sense, frankly. And you just degraded by a huge percentage the amount of conversion of the energy. So it's just a bad idea. Alright, so it's went from 10% losses to 20% losses. So just a huge degrade in the experiment. He's calling this an inelastic case, and that's the whole point. The point is it's supposed to be hard elastic, not inelastic. You don't want a bendable, crushable thing in the experiment anywhere. Nowhere in this whole analysis of this experiment was it ever talked about like the lever should crush or the car front should crush. Nowhere do we want anything crushing. So again, why he's calling it doing this inelastic thing, and he's calling that hard elastic. So hard elastic is the same as inelastic to him. It certainly isn't to me. Sticking is not bending or breaking or crushing. Sticking is different, okay? Hard elastic is not the same as inelastic. Alright, so he does the second trial, worse than the first, frankly. He got even more travel through, so even less of the first cart's energy actually got to the other cart, and you got this, gigantic dip in how much energy got to the second cart. So, clay, complete failure, complete evasion, complete nonsense. Why would you put clay on it? Okay, why would that occur to you be a good idea? Crush some clay. That won't interfere in any way. That won't absorb any energy, crushing clay. Play-Doh.
Again, the lever itself is quite low friction. The tracks are pretty low friction, so there shouldn't be a lot of external torques happening from just before to just after that collision. So in all of these cases, no matter what the specifics of how the collision goes, this angular momentum should be conserved. Okay, that's going to be one of the key things that we're testing. The kinetic energy, well, if I have an elastic collision or something close to an elastic collision, we should hopefully not lose too much kinetic energy. I'm thinking we're probably going to lose a little bit because we're not going to get a perfectly elastic collision. When we use the clay bumper, we're probably going to lose quite a bit more energy. We can check out that prediction, but in no case.
Really is unbelievable. So he's wasting a whole bunch of time measuring the angles of the bar after it's already pushed the cart. And you're just like, well, of course, it has some stored momentum left in it. That's the momentum you lose. That's the price you pay for moving the bar, is the bar doesn't going to just stop for no reason. It's not going to be able to get all of its energy into the cart because that would require it to somehow slow down or something. And it can't slow down. It can only push the cart the fastest speed it's going. It can't stop the cart. It can't pull back. It can't do any of that stuff. So its momentum is going to carry it through a full circle. I mean, technically, it should keep spinning, with the momentum it's already acquired. So I don't even understand what he's doing or why he's doing it. But yes, that's why the video is an hour and 43 minutes long, is because he's wasted so much time on this angular momentum nonsense. I can't for the life of me understand why this is the subject. The subject is how much energy goes in and how much energy comes out. That's the frickin' subject. The bar, you've already accounted for. You've already accounted that it's going to steal 10%. So now you know it steals 10%. Alright, so here's his data. You can't read any of it. I can't understand where the fuck is the goddamn velocities. These aren't the right velocities. I wrote, let's see, 587, 587. He's got the same numbers in here. I mean, that must be the masses. Yeah, so the first run was 44 and 37. He's got 4 here. Here's the 37, but he's just got a 4 here. 0.4. It's 0.44. You know, and so it doesn't. Nowhere in his chart can you just simply read the frickin' velocities. So yes, you get the masses. We don't get the velocities. He won't tell us the velocities here. I mean, this is before, after. This is the second card. So yeah, so there's a 4 missing here. It was 0.44. All right, well, let's see what he does to the second one. You know, we'll see. I mean, but it doesn't point out that, yes, the fact is it's very close to exactly what you should be getting. Now, his initial, let's go back to his original video, okay? His original video, his prediction was it bounces back with half the energy. So the cart goes in and it bounces back with half, and the other cart only leaves with half. That was his original prediction. So just recognize way off his original prediction. You know, if he won't admit that, then I guess I'll have to go get the clip, and I'll play the clip of him insisting that we can't do this test. The very test he did, he said you can't do it because it's not going to work. You can't get the energy from one cart into the other cart. Clearly, even with the spring on there, he almost did it. And without the spring and without clay, he would have done it again. Better. Oh, just such a, you know. I don't know why he doesn't give the number. So he's doing the how much kinetic energy was lost, and it's 9.9%. So not bad. So you should just say 9.9%. And it's the same for the momentum. So the momentum and the kinetic energy are the same because the masses are the same. I mean, duh. So both theories can survive this first experiment intact. Except his original prediction was that can't happen. That was his original prediction. So he's doing the clay one now, and he's talking about the angular momentum being conserved. And yes, we lost more. So yeah, it's not a good idea to do the experiment this way. 25% of the energy was lost. 25%. And you can point right to that lump of clay for the 14% of that 25%. So what the hell? I mean, obviously a defect, huge cheat in the experiment. Don't use the clay, obviously. But anyway, we're going to see how it will destroy the results of every single other experiment, because he's always going to be doing a conversion between a heavy cart and a light cart. And so he's always going to be killing enough of the momentum to justify the fact that the kinetic energy didn't increase. Well, the kinetic energy didn't increase because you actually didn't get anywhere near the total momentum of the cart into the other object. You didn't get him anywhere close. Alright, so here he talks some absolute crap. So this is pretty funny.
Actually false. You might say that from this data, if I were to just do the mass of 1 times the velocity of object 1, and then take that and compare it with the mass of object 1 times the velocity of 1 after the collision, mass of 2 times the velocity of 2 after the collision, when you add those up, you'll get something that matches pretty accurately. And that might lead you to think that linear momentum is being conserved in this case.
Okay, it obviously is. So let's just understand, it's obviously being conserved. The energy went in this way, it's going to come out that way, so it's coming out in completely opposite directions, all right, against his law, okay, his original prediction. So the evidence is glaring that his original prediction was garbage. Even with a spring on there, okay, it didn't bounce back. It's a 0.002 bounce back, almost nothing. So, yeah, you know. So let's see, let's just hear the crap he's going to spew.
It's still not being conserved because linear momentum, as we've demonstrated before, linear momentum has a direction to it. When the original card is going in to the camera's left, well, it's moving in a particular direction. That card...
It's motion in the universe, and that's all that matters. It's motion in the universe. All motion counts.
Basically stops, and it launches the other card in the opposite direction. If that other card is moving in the opposite direction, that is a different momentum. Momentum has direction. We can't just...
So he's saying somehow that we only gain the differential between those two things, or somehow we destroyed all the momentum, when, no, obviously you have something on wheels moving. Obviously. I mean, it's just so silly. This is like their work equation. This is no work, okay? Because I'm not moving anything. Nothing's moving, it's no work. I mean, it's just too silly. Too silly. I can't believe he's saying this.
The magnitudes of those momentum are going to be equal, because when we're using conservation of momentum, the direction matters.
To you. All right? For no good reason. To you, you think there's some sort of unmomentum. So somehow we unmomentumed and we made no momentum. So we lost almost all the momentum. So only 10% of the momentum was conserved in the deforming clay and in the movement of the lever. But all the other momentum was somehow destroyed magically. Even though we have a car going almost the same speed, leaving the experiment. And that's really all that matters. What went in and what comes out. That's all that matters. I just can't believe he's trying to defend the notion that somehow that experiment shows a lack of conservation of momentum. So he's actually saying the momentum was not conserved, that we lost 90% of the momentum was lost. That's his argument. Ridiculous. All right, so here's the data from the half mass, full mass, twice the distance, the classic of the lever experiment. And it looks like a gigantic crushing blow to momentum. But anyway, not much of a velocity increase. I would argue that, it's below the 0.4 even, and the reflection doesn't look big enough, frankly. But this is with the spring. So who knows what the spring did here. But anyway, so I guess I'll wait till I get the full numbers. All right, so my analysis of the numbers is that you lost a little bit more than 10% of the momentum. So we was hoping to lose just 10%. So we lost maybe 15. And obviously springs are, the whole, it just interferes with the transition, the movement of the migration of the energy from one object into the other object in this case, because of the fact that you're going in opposite directions. So the spring isn't going to help you any. It's just going to get in the way. So yeah, I stated in the original video, the original discussion, I really don't have any interest in these experiments because they are deliberately not conveying all the energy. Some of the energy staying in the object. You don't want any energy to stay in one object. You want all the energy to go into the other object. So it's against the whole idea, frankly. All right, so you might as well see this too. So this is bizarre. So this is with the clay. So obviously the more energy you're trying to convert, the more the clay is going to absorb. So this outcome is so crazy. I mean, it's actually the lighter car is going to go with less momentum, okay? It's not even going to go twice as fast. It's not even going to go with the same speed as the heavier car. Now, part of me says, oh, that's got to be a mistake. So, just looking at it, I guess we can do some of that.
Okay, so this is...
I mean, the blue car is going to go slower than the silver car. That's what the data collector says.
Half mass or double mass at half distance, the inelastic case, trial number 1. So let's see what we get here.
So he calls this the inelastic case, and what it's supposed to be is the hard elastic case, the no spring elastic case. But he didn't do that case. The case I wanted to see, he didn't do. So again, the silver car, the blue car is going to go slower than the silver car, even though it weighs half as much. Doesn't look slower, but whatever.
Okay, so just after
that's what the data says, right? So the first car comes in, the heavy car comes in, and the light car just doesn't. No, it's just a tremendous loss of momentum. Half the momentum was lost. Half of it. Half the momentum gone. More than half gone.
The collision, we've got a velocity 1 of 0.596 meters per second. Velocity 2 is essentially 0. And here we've got velocity 1, it just... Where do we want to find that one? We'll go with this one. Just barely bounces back with a velocity of negative 0.005 meters per second. Velocity 2 is 0.559 meters per second. So let's reset this. Okay, so this is double mass at half distance. Trial number 2 in the inelastic case. And let's take...
The case I would never have suggested. Yeah, the pointless, useless, can't tell you anything good case. And then look, it even makes the clay pointy. I mean, it's just so ridiculous.
Take some data.
So, it still looks faster than... Well, that looks slower, frankly. Yeah, hard to say. Look, he lost even more. So he lost 70%, 60% of the momentum was destroyed through some magical process. I wonder what it could have been. Where could 60% of the momentum go? Oh, yeah, that blob of clay. Oh, what a bad idea. All right, so useless. Useless experiment. Still talking about angular velocity. So at least he concedes it's 54.6% of the energy was lost. So, I mean, I don't understand the point of what he's doing at all. All you're supposed to do is make a comparison between momentum in, momentum out, kinetic energy in, kinetic energy out. That's all. But he doesn't want to do that. So maybe I'll just play the rest of this through. It's just going to be all these, there's no point. Springs and clay, these are not the experiment I wanted to do. It's not the one I wanted to see. So with the spring, you get, 1/3 the mass. So 1 to 3 mass ratio. So you can see, yes, the second cart leaves a little bit faster, but it's nowhere near 3 times faster. And the big problem is that, yes, you have a huge bounce. Okay, so half the momentum is in the bounce, and so the other object didn't get its full increase in velocity. So, but whatever. It's just not useful. All right, just sitting here watching this, there's no point. It's just, it's 2 experiments I don't want to see. But you're saying to yourself, okay, how did he come up with this clay idea? And he didn't try anything hard. So he didn't try to put anything more firm on the end of the cart to hit the lever with. Nothing occurred to him. He couldn't figure out anything else but a big blob of clay. And it's not even a consistent blob of clay, by the way, right? It's shaped every time he gets to reshape it into who knows what configuration. I mean, it's just so bad. Why would he conclude this is a good way to do the experiment? And you have to just wonder, he never tried just banging the cart into the lever. He never even tried it. Yeah, I don't think so. Yeah, I don't think so. All right, well, I'll play this little tiny bit because he's just trying to take shots, that somehow, look, we don't get any extra free kinetic energy. Yeah, because you threw away 66.4% of the momentum.
Once again, angular velocities match. It's closer to an inelastic collision since it's clay, so a lot of energy loss, but our velocity ratios are inside of the expected ranges. So notice, in none of these cases with the triple the mass at a third the distance are we getting any sign whatsoever that we're producing energy, that we have some free energy machine here.
So, yeah, because you've lost 66.4% of the energy. Yeah. God, amazing. Amazing that he would sit there and make this claim that somehow, look, it didn't happen. We didn't get extra kinetic energy. Yeah, but you didn't transfer the energy. You fucking plowed it into a blob of clay. You threw away half the energy molding clay rather than doing the experiment you were supposed to be doing. Oh, just so annoying. All right, so just as a curiosity, so now he's not even paying any attention to using the same mass ratios or any of that kind of stuff. So he's putting two equally massed carts, one at half the, hits at halfway, and the other one all the way out. So, and they're equal masses. And frankly, the result looks like he made free momentum. So you got to say to yourself, well, why should that experiment create free momentum, right? There's no reason for that to happen. So you got to wonder about his timing mechanism, that maybe it is a little bit off, because frankly, you can see on this chart that this line is above this line. They're equally massed carts, so the distance here should be the same as the distance here, frankly. Or you don't have the same total. This total has to equal what you'd pile on here. So if you took this and added this, that's more momentum, clearly. So, come on. You made free momentum? Come on. Yeah, come on. No, you didn't. I don't think you did, okay? So what are we going to blame for the extra momentum? The spring magically created extra momentum? Where did the extra momentum come from? Come on. I mean, it has to be extra kinetic energy also, because the cart is the same mass. So he made extra kinetic energy. It's a free kinetic energy outcome. This reflection has to be piled onto this blue part here. So it's a free kinetic energy too. So I wonder how he's going to explain that. Alright, so he's pretending there's no free momentum or free energy created, and it's clear in the results that if I add 282, which is the rebound, to the 408, so these are two motions going in the same direction, even though it has that one called a minus, it's in the same direction, it's 682. 682. I mean, it can't be 682 because you only started with 554. So he doesn't say anything about it. The 19% off is 19% in extra free energy way. You didn't lose 19%, you gained 19%. I don't even know why he doesn't even notice that. Because none of these things are actually comparing the thing he's supposed to be comparing, which is total kinetic energy versus total momentum. But no, we don't have those numbers. But clear, it's just clear. It goes in with 554, right? It weighs the same. The carts all weigh the same, so mass doesn't matter. So you start with 554, and then you end up with a velocity, a total velocity of 682. So, it's a huge increase in your momentum and kinetic energy. And he's not saying anything.
Inside the expected ranges, and actually pretty close to what we expect from this elastic case. Again, these percent differences in elastic, this is the elastic case, so those don't really apply. Let's look at trial 14.
See, nothing. Doesn't say a damn thing. You just made free kinetic energy, and you just made free momentum, and he doesn't say a damn thing. Obviously, he didn't do that, right? So we know there's something buggy here. Something's buggy. It's not working quite right, because you didn't make free momentum. You really didn't. Alright, might as well play this part. He says it again.
0.526 meters per second. Velocity of cart 1 after is negative 0.116 meters per second. Velocity of cart 2, 0.314. And the angular velocity is 0.349 radians per second. Matching.
Right. So right here again, you got way too much coming out than you put in. Oh, wait a minute. This is the clay example. Never mind. Okay. Continuing.
Angular momentous and a similar energy loss. Velocity ratios in the
gigantic energy loss, 60%, because of the clay, because of the thing that shouldn't be there, the thing I opposed having in the experiment, the thing I directly said, don't do anything stupid like that, nothing crushable.
Expected ranges. Again, all of this supports the classical understanding, the textbook understanding of physics, that this system is governed by conservation of angular momentum primarily, and then whether energy is conserved or not depends on what kind of bumper it's running into. And in no cases do we get an increase in energy. There's no free energy here.
Okay, so in this very experiment, he got free kinetic energy. I mean, realistically, you put 100 in this way, and you get 150 total going that way. Both carts are going that way with more momentum than you put the first cart in. Does anybody believe that's possible? That levers are capable of making this free motion in the universe? I can put this much in this way and I can get more momentum out? Come on. I mean, how incredible. I mean, there's got to be a point where you people say, okay, something's got to be wrong there. That can't happen. I can't get more kinetic. Again, it's more kinetic energy. It's free kinetic energy and free momentum because the carts weigh the same. All right, so these are all useless trials. So this one, he's doing uneven masses at the same distance. For what reason? I can't figure out why. All right, anyway. All right, just out of my own, what it appears, okay? That's all I can do so far. I guess I'll have to download this and do the frame rate crap. But it seems like the blue line is way underestimated as a velocity, okay? Because in this case, it seems clear that the lighter cart is going a lot faster, and it's barely going faster by this recording device's opinion. So his recording device says it's not going much faster at all, this little tiny bit, and it don't look nothing like that. So that might be a flaw in his technology. Yeah, it might be. It might account for the free momentum before. All right, so I think this is something he did previously. So he put this wooden dowel back in the experiment that goes through a whole different kind of center fulcrum. And it's clear that the center fulcrum really can't allow something to bend, okay, from one side to the other side. It's not really going to transfer the bend, okay? It can only bend to the fulcrum. It can't bend all the way to the other side. So, but whatever. Little sticking points, but I mean, it is kind of an important point that this isn't, you can't bend through the fulcrum. So in this wacky experiment, he lost just about half the energy, so almost half. With the springs, this is without the clay. Half the momentum gone. Oh, but it doesn't matter if it's springy. Well, apparently it does matter. Anyway. Alright, so he did a couple more of these, useless wooden lever with springs, and he didn't bother doing the clay ones. And this one, again, has extra momentum. And the only thing you can blame is the red cart, the far side velocity detector must be exaggerating velocities. Because, again, it doesn't make any sense. This is going to end up being a little bit extra momentum. Not much, but it's more than it started with. Well, let's go to the numbers and we'll see. It looks like it. But we know it sort of is extra momentum because we know we're supposed to automatically lose 10%. So even with the 10% losses, we're getting more momentum, which doesn't make any sense. All right, so I was right. It is free momentum again, free kinetic energy. In this case, both carts are the same mass. So he starts off with 463 as a velocity with the same mass. And he ends up with 500 even. So he gained, 43% more momentum. And that's in a system where you automatically lost 10%. So again, he made more than that. You could add another 50. So it's 100 free momentums, and they're free kinetic energies also. So just understand, that experiment made free kinetic energy because the rebound is in the same direction as the other side's direction. So, and frankly, for your kinetic energy thing, direction's not supposed to matter. It's more kinetic energy than you started with. So that's a problem. You can't admit it's a problem, then I don't know. You're a problem then. But that ain't supposed to happen. That's not physics' prediction. So, again, you have to concede, you have to have the 10% loss because the lever's moving. And this is the wooden dowel, so the loss is even higher. It's probably more like 15 or 20%. So, you know, you're talking about a rather substantial 20% increase in the momentum. That can't happen. All right, so I guess we'll play this part. It's just so full of shit. All right, so I'll make it less fast, but a little bit fast. Anyway, so here's his summing up. So I just figure this ought to be a real steaming pile of crap.
We learned here. We performed 20.
So he says we performed
26 trials on lever systems covering 13 different physical configurations.
And none of them what I described. Not one of them. Hard against hard elastic. I made it clear, we talked in person, I pointed it out, I described exactly, and you didn't do anything like what I described. And now you're going to claim that you proved me wrong, or you proved anybody who says levers do conserve momentum wrong. And you didn't do that. What you did was just show that your experimental technique must be broken because you made free kinetic energy and free momentum.
We demonstrated that it is the angular momentum.
So he didn't demonstrate why we should care about this angular momentum. He's just talking about the speed that the bar is moving after the object left. Who cares? That's just the leftover energy that's stealing energy from your experiment. Your car had to give that lever that extra pushing power, and it can't get rid of it. It can't give it to the car. It does have to consume it. So it does. Proving that the lever moves with a consistent speed doesn't prove anything.
Angular momentum value that is of key importance when considering the motion of these kinds of lever systems.
No, it isn't. The key importance is how fast is this thinking car moving? How fast was it moving? How much did it weigh when it went in? And what are you getting out? That's all that matters in this experiment. That's all that matters to a lever. You're just basically converting energy. You're saying I'm putting energy into this lever system and I'm going to see what kind of energy I get out of the lever system. That's all. This is just canardy evasion to be talking about some other bullshit as if we should care about some other bullshit. No, we just want to know what happens. I put a certain amount of work in. How much work do I get out?
Whenever we have a system where there are no external torques, angular momentum will be conserved. This is covered in any intro physics.
Again, he didn't measure the angular momentum of the lever as it had the masses on it. When it has the masses on it is sort of important. And again, all he's really saying is there has to be a consistency between how you take the energy from one side and how you apply it to the other side. Well, of course there has to be, because it's a rigid lever. It doesn't have a choice.
Textbook, and it does apply to these lever cases. It doesn't matter whether we use springs for the bumper.
So he didn't say anything about this, frankly. Okay, I mean, in the I'm going to do a lever experiment video, he didn't explain how. Oh yeah, well this is just an angular momentum experiment. It's not going to have anything to do with anything else. And let's understand his prediction. He got the first experiment prediction completely wrong. He said if you'd use the equal masses at equal distance, you're going to get half of the energy is going to bounce back. And even with a spring, it didn't happen.
Or whether we use clay for the bumper. It doesn't matter whether we use different...
A clay for the bumper. Yeah, well, it doesn't matter whether we use, what, maybe a ball bearing? Maybe that would have been a good idea.
Masses thrown at different distances. It doesn't matter whether the bar has some flex to it. In all of these cases, when we measure the initial angular momentum and the final angular momentum...
Of the bar. He's not measuring the momentum of the objects you're actually throwing. So again, what the bar is left with, who cares? Who cares what amount of momentum the bar has? It really isn't that important.
We find very, very close agreement, again, in all of these different cases.
Yes, so the bar always absorbs about the same amount of energy. Who cares?
As long As there is no external torque applied to this system, the angular momentum is going to be conserved. And that matched the data that we got.
Oh, whatever. So this is just such an evasion of the real subject, which is a challenge to the kinetic energy theory and pointing out that levers either conserve kinetic energy or they conserve momentum. And what you did was evade that experiment, because that experiment can only be done with hard elastic objects.
Again, this isn't just a claim. This is experimentally verified.
Oh, it's just bullshit. It's just absolute bullshit that you would pretend that you have verified anything or proven anything or debunked anything or any of that. This is just such fake science. You've cheated the truth all over the place here. Clay. I'll put a deformable object and then we'll transfer the energy. That's like saying I'm going to a car crash and I'm going to put an airbag in front of my car. No, it's worse than that, right? Because the airbag is elastic. So he's just saying, look, we're going to put metal tin cans in front of my car, and then I'm going to go try to crush somebody else's car with it. Well, that ain't going to happen. You're not going to be able to transfer any energy to anybody because you're just going to crush cans. And you know it. This is just too silly to have to argue. Clay was totally useless experiment.
With these trials to a high degree of accuracy.
Oh, again, this high degree of accuracy, except for the gigantic losses. Yeah, it's very accurate if you don't mind 33.7% lost energy.
Of the 26 trials that we did.
26 useless experiments, not one of them as described in the initial conversation. So we didn't bother doing it the way we said we were going to do it. Instead, we just did our way to prove our point. Our narrow little nothing point that couldn't mean anything to anybody really interested in this subject.
The initial and final angular momenta matched to within 5%.
Oh, it's disgusting that you could say this shit.
For, again, 22...
You have 60... What was the highest losses? Like 69% of the energy was lost. In one case, 69% of the energy lost. The momentum.
Of those 26 trials. And a full half of the trials had those initial and final angular momentas matching to within 2.5%. There was only a single trial where the initial and final angular momentas were off by more than 10%.
So there were 4 trials altogether that created free kinetic energy and free momentum.
And it was just over 10%, and that was the case where the cart was very, very close to the lever, so it was very, very sensitive to small changes in that position. In each and every case that we looked at, the measured final velocities of carts 1 and 2 were within the expected ranges between the perfectly elastic case and the completely inelastic case.
I don't even know why I would compare those two cases. What does that have to do with anything? Why would I compare crushing fenders when I'm trying to convey the energy? I'm trying to get the energy into the other object. Why would I put a deformable in front of my cart? It's not going to happen then. So it's like what? It's like putting Twinkies on a bowling ball. I don't know what it is. It's worse. It's like putting crumpled up paper on a bowling ball. Yeah, it's not going to knock down the pins as well.
As predicted by standard physics principles. In every scenario where we used both spring bumpers...
So he keeps implying that he actually did the experiment. Yes, we did it. We did the experiment you described. It's just a lie.
And clay bumpers, where we did the same...
Clay bumpers. What the fuck is a clay bumper? What the hell is that? It's not a bumper. It's an absorber. It doesn't... Things don't bump off of clay.
Kind of setup of just changing which bumpers we were using. Using the spring bumpers got us closer to the elastic case. So if we go to some of these cases over here, using the spring bumpers, we were a lot closer to the elastic case. Using the clay bumpers, we were a lot closer.
Duh. Yeah, you want to throw away 69% of the energy, put a blob of clay in front of your cart. I just can't believe he's serious. He seriously thinks this is a fair performance of the experiment I described. That this is a fair duplication of my experiment. Ugh, it's disgusting.
to the inelastic case. Not super close because it...
So I'll just play my original video, right? The conversation where I said, I really don't care about springs. I don't even want to hear about springs. The last thing I want to see the cart do is bounce. That's the last thing I want to see. I'm trying to get energy into something. The last thing I want to see is a bounce.
Didn't hit.
It's like hitting somebody with a bullet and you want to kill them. Well, the last thing you want to see is your bullet bouncing off. Because it ain't going to work then.
And stick completely to the cart, but we did get a lot closer. There were 0 cases where we saw...
Okay, so that's a lie. So right there he's lying. There weren't 0 cases. There were 4 cases where you created free momentum and free kinetic energy.
Any increase in energy from the system.
So that's just bullshit. In one case, the cart kept going. The other case, the car bounced back. Either way you look at it, you have to count it, all right, as energy. So you can't play your minus plus bullshit game, okay? Because in one case, the extra momentum went forward. In the other case, it went backwards. So you have to add it to the other stuff. So you had 2 carts going this way, or you have 1 cart going this way and 1 cart going that way. That's what you have going out. What you had going out has more momentum than what you put in. And it's the same mass cart, so that means it has more kinetic energy.
Even when we have these cases where I'm throwing a high mass object closer to the fulcrum point, so the 3 times the mass at 1/3 the distance, we did not see any evidence whatsoever.
So that's just wrong.
For an increase in kinetic energy. Linear momentum is also...
Obviously, in the other case, the clay cases, you didn't see it because the clay absorbed it all. 69%.
Also not conserved in these lever systems because there is an external force at the fulcrum point, and the linear momentum of a system is only conserved when there are...
So again, there is nothing. Fulcrums, the whole idea is just the fulcrum doesn't move. That's the whole point. It can't absorb anything because it doesn't move.
Are no external forces. This is what makes a model scientific.
No, this is what makes propaganda and bullshit. Okay, this is not. There's nothing scientific about your analysis. You really haven't done it fair, and you haven't done it within, some sort of rational context of explanation. And the fact is, you just can't explain the creation of free kinetic energy or free momentum. And you made both.
The standard physics principles that you learn about in any physics textbook or any intro physics...
Well, whatever. Again, your textbook's full of the nonsense. So again, where's your textbook show you the experiment where it takes 9 times the fuel to go 3 times as fast? Where did they do that experiment and show us that truth? Oh, that's right, nowhere.
Of course, things like Newton's laws, conservation of energy.
Again, lying about who Newton was. Newton didn't believe in your theory. He didn't believe what you're talking about. He didn't think you were right. So quit pretending he was on your side, because he wasn't. He clearly didn't think it takes 9 times the fuel to go 3 times as fast, and he plainly stated, that he thought it takes 3 times the fuel to go 3 times as fast.
Conservation of momentum, conservation of angular momentum, and a whole bunch of others. These principles, when properly understood and properly applied...
So were they understood or applied? No. This wasn't about angular momentum. This was about what you put into an experiment and what you get out of it. You got a black box called your experiment. You put a certain amount of something into it, and you're expecting to get the same thing out of it. And that's the law of conservation, and you violated it all over the place.
Allow us to build predictive models of how physical systems will behave so we can make testable predictions for experiments and observations.
Right, and your prediction in the past was that equal masses one of them will bounce, and the other one will come out at half the speed. That was your prediction, completely wrong.
Observations. We keep the principles that survive repeated testing, and we discard...
Again, where's the repeated testing? You haven't tested it taking twice the fuel to go 4 times as fast, or 9 times the fuel to go 3 times as fast, or 16 times the fuel to go 4 times as fast. You haven't tested anything. Nothing. You're just a fibber and a propagandist. The biggest piece of evidence you could produce would be evidence of this fuel problem, and you can't show even the 2 to 4 thing.
We discard those that do not hold up to scrutiny.
You don't apply any scrutiny, you just evade the scrutiny, you evade the argument, okay? Just as you evaded everything, every caution I said about this experiment, you just ignored everything I said.
In these experiments, we have demonstrated, again, not claimed, but...
Oh, you haven't demonstrated. You've demonstrated you're a crook and a thief if you're saying this was my experiment. So again, that's just a lie. I plainly asserted what I expected to see, okay? And I didn't expect to see clay on the goddamn cart.
Demonstrated that angular momentum accurately describes the behavior of these systems, as well as...
Yeah, again, he didn't show that at all. Why do I care about the momentum of the lever after the objects have left? Why would that matter to me? That's just showing me how much I lost. The other cart had to make the lever move. So the lever's still moving. That means that's energy neither cart has. How does that demonstrate anything? So all you demonstrated was you can expect to lose about the same amount moving the lever.
As conservation of energy in the elastic cases. Again, if I go to more of the elastic cases, we were much closer to having this energy conservation. So these principles of angular momentum and conservation of energy, those are ones to keep. Conversely, we have demonstrated that these levers do not violate conservation of energy.
All right, you didn't demonstrate, but you didn't do that experiment. Plainly. Come on, plainly you didn't do it. So you're just lying to say you showed that these elastic, hard elastic, not rubber elastic, not spring elastic, hard elastic objects won't conserve the momentum. You didn't show it because you didn't do the experiment. You evaded it clearly.
So that idea can be safely discarded.
Oh, yeah, right, because you didn't do the experiment. I mean, it can be safely understood that you did do it and you found that, yes, it doesn't work. Your theory fails. It's clear. You know, he didn't just all of a sudden say, I'll put clay on the cart, right? That was a desperate effort because he just said nothing. Oh, anything hard I put on this cart ends up making all this extra energy. So what am I going to do? Oh, I'll have to come up with some kind of mushy stuff to put in front of the cart so I can absorb all the energy and destroy the experiment. Come on. It's ridiculous on its face. The carts cannot move, okay? They're stuck in a track. You put clay on it, and it hits the frickin' lever, and it's got to move across. It's got to slide across the lever. The lever's going to get a little bit longer. You're going to be hitting a different point of the lever. Clay? Come on. And again, I said right from the beginning, you don't need anything sticky. The cart shouldn't bounce. If you do the frickin' experiment correctly, the first cart, all of its energy should be absorbed. The lever should absorb all of its energy. It won't bounce and it won't keep going. It should absorb all the energy if you pick the right locations. I said that right from the very beginning, and you just ignored all of that technical detail. You ignored understanding that as the lever turns, it's actually changing the length of the arm, you know. And right, the carts were pushed by a lever that runs out, basically, right? It's pushing on the cart, and the lever basically runs out. The cart leaves before the lever can give it more pushing because it's already moved away from the lever far enough that the lever can't reach it anymore. And probably you should have used a point, not the very end of the lever. You didn't even do that.
So I hope that this was interesting. This one did take a lot of work, and
yeah, I have to say you did do your work, but it's all this fake physics. It's just more contriving physics. You worked really hard faking an experiment, pretty much faking a piece of propaganda, doing nothing like the experiment I described. And he didn't do the experiment I described, right? There's no doubt about it. He didn't do it.
I know that this is very, very long. Thank you if you watched the entire thing, or if you just watched a part of it, thank you as well. As always, I try to answer questions in the comments. When you're answering questions in the comments, please try to be respectful and courteous.
Yeah, what? Yeah, whatever. Yeah, your commenters won't be respectful. They'll be rude and obnoxious, and you won't do a damn thing about it. So, again, I'll start doing rag comments tit for tat. You want me to just change all the ones that are pointed at me, and I'll just write the same shit pointed at you? Right? I don't have any interest in interacting with your commentors, you know. But if you're going to allow them to do whatever the fuck they feel like doing, then I'm going to have to, you know, treat you with the same discourtesy. Fucker. So anyway, what a pile of shit. I mean, declare victory when he didn't do the experiment. I mean, and even look, the simple truth is mindless marbles, or some other guy already pointed out, well, why don't you, earlier when he did the other experiments and showed us the preview, they were already complaining, take that rubber shit off, take that spring shit off, do a hard elastic experiment. Didn't do it.
To others, and again, thank you for watching, and we'll see you in the next video.
Alright, so that's enough. It's, an hour's worth. Ugh, but whatever. So I don't know if I'll keep this listed. I don't know what I'll do with videos. There's just no point in, talking to 100 people. So I really have to work on that part before there's any purpose in making videos.